in this segment, I'm going to be talking about another type of electrochemical sensor that has become pretty popular, and these are kind of Aptamer-based sensors. And this work, if you want to read more about them, has largely, a lot of the techniques were developed in Chem and Plaxico's lab, and then other people pushing them to neurochemistry are people like involved with, like Ann Andrews has a team of people who have been working on Aptamer-based sensors. And so, again, this is based on the idea that short lengths of nucleic acids, typically DNA, but it can be RNA, will often bind to biological targets. So we're going to get some sort of selective binding. And it's not really obvious how to do that. So to make an aptamer, they use a process called Celex. And it's this process where basically you throw in, I don't know, 20,000 little bits of DNA, and then you have maybe your target attached to a bead or something like that. See, allow them to bind, wash out anything that didn't bind, take the stuff off the target, off the beads, kind of see what you have, and then, make things that look like that and repeat. And so they'll do cycle after cycle of kind of binding, washing out that doesn't bind, that kind of thing, to find the best aptamers. And so there's people who kind of specialize in the aptamer development. So it's not super easy, you gotta have the right equipment, and depending on what technique the harder part can be like kind of like the PCR, to amplify what you got and see what and those kind of crazy things. But yeah, so they'll do these Celex, and they'll make aptamers, and they can make them for, again, a variety of different analytes. And so they can make them for most of the small molecules we like to look at. So almost all of the electrodes, and I'm only going to, again, talk about electrochemistry, Aptamer-based sensors. You can do other data detection, fluorescence, that kind of thing. But almost all of these for a electrochemistry, they start with a gold electrode. And they start with a gold electrode because it's highly known that you can bind thiols to gold, and then those thiols can bind, you can do a bond pretty easily to make DNA. They'll cap off the rest of the thiols with just like an OH group. And so, again, you'll have gold with thiol chemistry, and you'll have DNA. And at the end of the DNA, they'll have a reporter molecule. So that R here is my reporter molecule. And typically when it's unbound, like what I just drew there, that reporter molecule will be floating all around, but it's typically not particularly close to the surface. And this reporter molecule, I should mention, for all of this to work, has to be electroactive. And by far, their favorite reporter molecule is methylene blue. They can use X, Y, Z, and it's like, oh, you can they love methylene blue. So it must be the strongest detection. So what happens when you have target come in and interact there? I'm too lazy to draw another electrode, so we'll just kind of like draw it. Well, that's a really bad way of drawing DNA. Maybe our helix better. Something like that. And now it will bind and kind of usually change configurations around the target. And so the target molecule, as it binds to it, will change the configuration of the DNA. And I purposely drew it so now, with this design, the reporter molecule is near the surface. And so now, if we were doing, say, amperometry, which is what they would typically be doing, all right, so they're going to apply a voltage and measure a current, and the current is going to come from, again, oxidizing typically that methylene blue. So again, when it's out here, you don't get much current. When you have target, that one is near the surface, and you can get current. And so that's, as I said, the real basics of Aptamer kind of based sensor. So if you were to kind of look at it, it is quantitative, but you have to remember that this is largely going to look like kind of enzyme kinetics. So you'll have a concentration of your target, which I put T over here, and you'll have whatever your signal, your current is, and you're going to get a curve, right? That looks like that, right? So this is what they call a Hill-Langmuir isotherm. Again, that looks very similar to things that you find in enzymes and other kind of things in biology. So not exactly linear. If you only did this point, you could probably make it a line, right? Kind of thing. But you need to know your range. Hint, hint. Range is always important in analytical chemistry, right? So again, but they usually have decent ranges. And what they're trying to do, again, is you can try and change your aptamer based on like the affinity kind of for binding and that kind of thing. So it takes a little bit to get a right aptamer for this, because it's not just that it needs to bind the target, it needs to bind the target with a conformational change that'll do what you want. So it's like, it's not just that every aptamer that comes out of CLEX might be appropriate for these types of sensors. But that's in general what they do. And like enzyme sensors, this ends up being a fairly general platform, right? If you can make the right aptamer, as I said, that's going to bind correctly and do that conformational change for a molecule, like once you know how to put it on a gold sensor, all of that, you've got your reporters, et cetera, you can work pretty well. But the other thing that they'll do, while I drew this like really easy, like the reporter goes at the end, it may not. You might hang it off the side or something, depending on what conformational change. So where you put that reporter, and how big this kind of, the size of this and the shape of this are all things that you can kind of change as far as that goes. Okay, so let's again look at a chart real quick for some of the advantages and disadvantages. And again, I don't look at this as an FSCV is better, I just like to compare back to our direct electrochemistry, which is what my lab primarily does. So this has high temporal resolution, because if we do amperometry, right, we can go at like 500 hertz or something, right? We can make many measurements per second, and so that is usually good. It is very selective. Again, they can get like an aptamer, for instance, that can select dopamine over norepinephrine. We aren't that good at FSCV, right? But they're just that one extra functional group. They're going to win on selectivity. I got this out of a Kevin Plaxo, miniaturizable. I don't know how to spell that. That's what they claim. You want to know what their miniaturizable is? I was looking at a table. He had a very nice table in one of his things. 300 microns. I actually talked a lot to Kevin Plaxo recently at a meeting, and he was saying that you just need a certain number of electrons in current, enough of these to bind. And so going down to the 5 to 7 micron level is just not super easy for them with these kind of sensors. So they are not on the same scale as we are on, but they are on kind of a scale where, that's the same size as an optical fiber that people put in the brain, et cetera, that people will use. I would say the greatest use of these right now, again, is not currently, although people are doing it, electrochemical detection in the brain as much as clinical use. So he has sensors for all of the antibiotics and things like vancomycin. If you get too much in your bloodstream, it can be poisonous, right? So that's what they're trying to. They're actually trying to develop a company around this, but that's the first one they're going to do, right? Because they can say, oh, in a clinical setting, if you could continuously measure the IV, the blood concentration of this antibiotic, you could keep it in the range that's helpful as an antibiotic, but not in the range where it becomes toxic if it's too much, right? You could dial it back if you kind of had a real-time understanding of what was there. He also has sensors for things like, so that's that. Maybe I'll just make my list of what we can make, what we can do. Antibiotics. He can do the drugs of abuse, so I'm really interested in maybe trying to use the cocaine sensor at some point in time. It's not super small, but again, so forensic applications, that kind of thing, they can do that. And as I said, they can measure things with amperometry in plasma, blood, brain, urine. So they're pretty good in biological fluids. And as I said, there have been some examples of in vivo. I'm trying to go there. The disadvantage is always the efficiency of your aptamers, right? I told you, Celex gives you just what binds, then you gotta go a step further and have what binds usefully for a sensor, which is more trial and error. So while it's a theoretically generalizable platform, it's not super easy to be like, tomorrow I want to do a different thing. I'll just, see what the Celex people will give me and it'll work. It's not quite so easy as that. This leads to kind of things about measurement, duration, and kind of how long they can last, especially kind of stability. So when if you were to try an aptamer in an in vivo experiment, this is going to be your signal, and this is going to be time. Like once you implant it, like any electrode, you're going to get tissue fouling, right? And so if this is your theoretical best signal you can get out of it, right, you'll get some tissue fouling. Now that happens with FSCV too, and we hate to admit it, but it's like 50% of our signal that we lose, just from stuff gunking it up. And so they're going to have stuff gunk up their signal too. But, if this is theoretically what you could get in tissue, the problem is, they also typically get something that looks like this. And this is their aptamer layer breakdown. So again, your body is full of little DNases that want to chomp up DNA. Right? And so other things that will break down that layer of aptamers, and once you lose your layer of aptamer, it's gone. Like if you lose a DNA, then it's gone. And so this has been tough stability-wise because they suffer from background drift. Now, I sympathize because we suffer from background drift too in the FSCV field. So again, I don't want to throw anybody under the bus too much, but the background tends to drift a little bit. And if you left it for really long, I don't think that anybody yet has gotten to the point where you can make a chronic, sensor you can put in for a week or something like that. Can they do 6 hours? Yeah. Right? So you want to do a cute one-day experiment? Fine. Longer term, you're going to have to solve this maybe with a coating or a polymer, or something else to save your poor DNA from other things in the brain. Okay, so this is all based on kind of, as I said, things I've read about Kevin Plasko's work. You can do another type of measurement, which is impedance. And impedance, you're just measuring basically the resistance of the electrode, the impedance of the electrode. So if you had an electrode, so if you have your electrode, I meant to draw it the other way. Let's do it this way. All right, you have your aptamers on it, and then they bind to the target. Not supposed to be target. Notice I left off the reporter here. We don't need it. So for impedance, again, as we add target to the electrode, we will change the impedance of the electrode. And so an impedance measurement is not a voltammetry measurement, it's just measuring kind of a resistance. So as we add, and we were to put more target, we change the impedance. Here's the problem. Impedance is very sensitive to other things that absorb. So the problem is you don't go in vivo doing impedance because I just told you, okay, I bound my target and then I got a bunch of protein on it too, and that whacked out the impedance, because it changed the resistance of my electrode. And it's super hard to tell the difference between a tiny little target binding and the big old protein that just absorbed my electrode. So clinically, if you had a pretty clean sample, impedance would work really well. Like, if you had you could take your sample out, but you wouldn't want to put this in blood or something like that. Just too much stuff around. Urine might work because it's a pretty clean sample. And so it depends on the application whether you want to go to impedance, but it's awfully hard to think we're going to go to the brain with impedance because, again, anything else that's going to gunk up your electrode or stick to your electrode is going to change impedance as well. And the advantage of amperometry, again, is that you're detecting a molecule selectively. And so those proteins, they may still gunk up your surface, but they're probably not going to have a redox potential that you're going to measure. So, your selectivity will go down, but they won't infect that. Okay, so this is like the traditional Aptamer basis electrodes, and now we will challenge my artistic skills to talk about FETs. So there's another type of sensor that you can make. And so we're gonna make, I'm gonna die if I try to make these look three-dimensional. So imagine these are all three-dimensional materials, but I can't do it. I draw them as like two-dimensional materials. I tried to make it three-dimensional, it looks horrible in my drawing. So in a FET, this is a basic setup of a FET. You have a source material, a drain, that's supposed to be a D, not a P, and then you'll have some sort of semiconductor. In this case, for the Andy Andrews group, at least the paper I read, it was indium oxide. And this is a really thin kind of layer here. And then they had SiO2 as an insulator. And so here you're kind of applying a voltage and trying to get a current to flow. I'll use my orange marker. A current to flow through the semiconductor from the source to the drain so that the device will conduct. And so all these things also have a gate. And you're like, oh, you didn't draw a gate. I didn't draw a gate because in this case they have what they call a liquid gate. So that's a drop of liquid, probably some sort of aqueous solution there. And so what they're going to do is in the place between this, they were going to have their aptamers attached to the surface. And so they have their DNA attached to the surface. And again, if a target comes in, some sort of target comes in, it's going to change configurations and go around the target and look something like that. So all of these, as I said, work by making like a charge layer kind of here that either pulls the electrons through kind of thing. And so when the target binds, you change the charge on the surface and it changes how much current you get, or they actually, most of theirs were in millivolts, so I think it's how much voltage they have to apply to get the current to flow. But as I said, there's always an electrode here and an electrode here. As I said, you're going to apply a voltage between them and you're going to have a current flowing if you have the right conditions. So under normal conditions, maybe the current doesn't flow, but if we get enough target in there, it will. Again, so the curves that you get are like the drain source current versus the gate source. As I said, this whole thing is the gate. The gate source. Again, there's standard kind of curves that you'll get. But again, if you're too low on the gate source voltage, this is negative and this is positive, you won't get any current, and then all of a sudden, you know, you'll get the current to shoot up. And so as I said, and not just applying a voltage here, but actually using this to trap things that are charged. That's as far as I'm going to go in my thing of FETs. I could do better. I used to teach this in my analytical class. But this is a standard technology. Maybe I'll put it that way. We analytical chemists didn't invent FETs, right? You know, FETs have been out there, you know, used in the electronics world for a while. What the analytical chemists found out is that they could gate them using molecules, right? You know, good old, you know, electronics people just use voltage. You know, they just apply voltage, you know, and we're gonna use a molecule to gate it. And so this is, as I said, an example of some new technology. Advantages of FETs, they are usually super high sensitivity, like, you know, like picomolar kind of things, right? You know, they'd be an order of magnitude better than, you know, or maybe even 2 orders of magnitude better than what you could get with like FSCV. Because if you get a good device, as I said, you don't need a lot of, they're pretty small, right? You know, they miniaturize these like electronic printing, you know, so there's not a lot of these here, but you don't need a lot of molecules to change the gate source current. In fact, you have to actually worry in analytical chemistry that you're not in the range you want to be. So I told you aptamers have curves, right? Binding curves. They still have binding curves here too. And you don't want to be here if that's your physiological range. So you have to worry a little bit, you know, about being in range, out of range with the FETs kind of thing. These are, again, typically made on MEMS devices. So they're all, you know, the FETs, etc. you can print, you know, hundreds or thousands of them at a time. So it really lends itself to the idea of arrays or that kind of thing. Again, it's all with the electronics technology, which is great because it's super well developed for other applications. Let's just put it that way. The time resolution right now is seconds, which is pretty good. It's not yet sub-second, and I'm not super well versed in what it would take to get there, but that I got out of an Ian Andrews paper, which she's developing these. They're not yet to sub-second time resolution. And so they've made these now for, again, they've started with some of the small molecules that we know and love, norepinephrine, dopamine, serotonin, that kind of thing. And as I said, they will get selectivity between, say, dopamine and norepinephrine. Same issue if you want to go in vivo of getting them to be stable and getting them not to have background changes. And as I said, you know, you can detect currents through here, but a lot of this is still an impedance, kind of same thing as I talked about with impedance, that if you get some other thing that comes and binds to your, you know, surface here in the gate, it could change the charge, which could change the performance of the FET. And so they're pretty sensitive to fouling. So again, they've been working on this platform for a while. They've finally gotten just a couple of kind of in vivo experiments used as well. The other problem, and maybe this limits some of the time resolution, is the binding, how the off rates of the binding. So you want it to bind, you want to get a different signal, you want it to let it go, right? So you can get a down part. And the initial binding is pretty good, but if you want a high signal, you want it to bind and hold on, but then you don't get very good off kinetics. So one of the things I've not seen a lot of is them like doing our typical squares that we do for FSCV. I'd love to see what the off kinetics look like, because it's a real issue with how you design the aptamers. If they bind too tight, it'll bind it, but it'll never let it go. And we want kind of a reversible sensor that's going to bind it and let it go as well.